The last lecture we were discussing the decomposition theorem of a vector field, wherein we have started that given any vector field A which is well behaved everywhere and A together with its surface integration goes to 0 in asymptotic region, then one can write the vector A at every point as a longitudinal plus a transverse part. The longitudinal part has zero curl, which suggests that this can be written as the gradient of the scalar potential alpha, and the transverse part has zero divergence, which suggests that it can be written as a curl of a vector point function called a vector potential. Furthermore, these potentials are obtained, the alpha, the scalar potential is obtained from the source part of the vector, while the vector potential is obtained from the vertex part of A. In case of electrostatics, we have seen that curl of E is 0. Since curl of E is 0, there is no vector potential for electrostatic field, but for electrostatic field has non-zero divergence, so it is represented by scalar potential only. The magnetic field is always have divergence B is equal to 0, so it is always represented by curl of the vector potential. On the other hand, electrodynamic field, for electrodynamic field, it is divergence B is 0 still, and curl B is equal to minus del E del T, so it is non-zero, and divergence E is not equal to 0 and curl of E is not equal to 0. So for electrodynamic field, E will have scalar as well as vector potential, and in fact E can be written as minus grad phi minus del A del T. But since this is always 0, we can represent it in terms of a vector potential. B is equal to curl of A. That's all about the recapitulation of decomposition theorem. Now we shall go to uniqueness theorem. In decomposition theorem, we have seen how given a vector A can be decomposed into parts. And uniqueness theorem says that if the divergence of and curl of a vector field is specified on a given volume and on its boundary, then the field is defined uniquely. That is, if divergence of A and curl of A are given, that is, divergence of A and curl of A specifies A uniquely. So we consider again a certain volume in which divergence A and curl A are specified. To prove this theorem, let us consider there are two vector fields A1 and A2 having the same curl. So we have two vector field A1 and A2 which has the same curl, and we have the same divergence too. Still we demand that A1 and A2 are different. Curl of D is equal to 0, where D vector is the difference vector, is the A1 vector minus A2 vector, and this defines that divergence of D is equal to 0. Since curl D is equal to 0, it readily suggests that one can write D as the gradient of some scalar point function psi, and when we use this on we see that these are the conditions. Now recall Green's first identity. Green's first identity is f grad z This is Green's first identity. We use let f is equal to g is equal to psi. So we apply Green's first identity to this. Then we get now first thing, due to this relation this is 0, and again if we take the boundary if we take the boundary S to lie far away in the asymptotic region, in which case A1, A2 both goes to 0, and in which case this as well as this goes to 0. So when S tends to infinity, we have the surface integration then we have note that it is the magnitude of a vector square, so it is an essentially positive quantity and volume element is always non-negative. So this quantity is 0 means the integrand itself is 0, that is and this means that D is equal to 0, that is A1 is equal to A2. So we see that if we specify the divergence and curl of a vector field, then the vector is specified uniquely. Another way of this part can also be looked upon in a different way. We are supplied with the value of divergence and curl everywhere on the volume as well as on the surface. At the surface, A1 is equal to A2, that means this is 0 on the surface, so this part is also 0. So even if you do not apply this condition, this part is 0, and this defines that the vector can uniquely be defined by its value of divergence and curl. And we shall see that in electromagnetic theorem, which was proposed by Maxwell, the divergence and curl of the electric and magnetic fields are supplied. That is, the specification of the electric and magnetic field as done by Maxwell through his Maxwell's equations are sufficient to describe the vector fields. With this, we end our discussion on decomposition theorem, and now we switch over to a brief discussion on curvilinear coordinate system. We shall make a very brief description of curvilinear coordinate system. As a first example, we consider spherical polar coordinate system, that is r theta phi coordinate system. Now an elementary length is given by, if we have two neighboring points having coordinates r and r plus dr, theta and theta plus d theta, and phi plus d phi, then their separation is given by r cap dr, theta cap r d theta plus phi cap r sin theta d phi. We can get the unit vector along r cap, theta cap and phi cap. They are orthogonal, that means r cap dot theta cap is equal to theta cap dot phi cap is equal to phi cap dot r cap is equal to 0. They are right-handed, means this is the right-handed nature, this is orthogonal nature, this is right-handed nature. Now if we consider the surface area, r is equal to constant, for r is equal to constant surface area, so dsr is given by r square sin theta d theta d phi on theta is equal to constant surface. The surface area is given by theta cap r sin theta dr d phi, and on the phi is equal to constant surface try to visualize these things physically. As for example, r is equal to constant surface means it is the area element on the surface of a sphere. R is equal in spherical polar coordinate system, r is equal to constant is a sphere centered at the origin and having radius r. So this is the area element between theta and theta plus d theta and phi plus d phi. If you set theta is equal to constant, you will get a right circular right circular cone with its vertex at origin and opening along the positive z-axis and with semi-vertical angle theta, and it is the area element on a right circular cone. So this is an area element on the sphere surface. This is the area element on the right circular cone. And phi is equal to constant. Phi is equal to constant is a plane which passes through the z-axis, and it is the area element on this plane. This is the meridional plane. And we know the volume integration. Volume part is also known. Volume part is r square sin theta dr d theta d phi, where r ranges from 0 to infinity, theta from 0 to pi from 0 to 2 pi. If we will try to see how this looks like, r cap is directed radially outward, theta cap is a semicircle, theta cap and phi cap is a circle in xy plane. If we consider the intersection of two phi is equal to constant surface, means this surface and this surface, you will get the direction along which phi increases. So these are the increasing direction. As for example, r is equal to constant surface is a surface on which r is constant and theta phi varies, and this is a sphere, and theta is equal to constant surface on which r and phi changes, and this is a right circular cone. So if we see, this is the sphere and we have a right circular cone. They intersect along this line. This is the direction along which phi increases. So these are the coordinate axes. And such things can also be studied with cylindrical coordinate system, rho phi z. Only thing is that in spherical polar coordinate system, the position vector of a point r is given by r cap into r, but in rho phi z coordinate system, the position vector of a point is given by rho cap times rho plus k cap z. Keep it in mind, this will be your, and rho is equal to constant surface is a cylinder surface, phi is equal to constant is a plane, and z is equal to constant is a plane parallel to the xy plane. So with this brief introduction to curvilinear coordinate system, we end our discussion on the preliminary mathematical topics. In the next class onwards, we shall discuss Dirac delta function, which is not a preliminary requisite, it is included in your syllabus. So we shall discuss Dirac delta function in detail, and we shall study its useful form properties, and we shall see that the term that we have evaluated T1 in connection with decomposition theorem can very easily be calculated by using the property of Dirac delta function.